We know a lot of microscopic and macroscopic forms of energy: kinetic energy, potential energy, heat energy, internal energy, all the different forms of energy that we know. Work energy, for example, cannot be created or destroyed. They only change forms. And the conservation of energy principle says that the net change in the total energy of a system is equal to the difference between the total energy entering and the total energy leaving the system during that process. So total energy entering minus total energy leaving is equal to the change. Well, that sounds awfully, practical. It just says delta E of the system is equal to E in minus E out. Makes sense because no energy can be created or destroyed. Here it is right here. That relationship is called an energy balance, or a first law energy balance, I like to always call it. So the change of energy in a system can be defined as the first law energy balance. Energy change equals final state minus initial state. Delta E equals E final minus E initial, or E2 minus E1. I'm just saying it over and over and over again in different ways. If I do an illustration of this, then I can see it a little bit more clearly. So let's take some really simple forms of energy and take a look at a system and apply this delta E conservation of energy, first law energy balance. My first thing I have to do in a thermodynamics problem is draw the system. I have to define where is the system, where are the surroundings, and what is the boundary. It's a good idea to label anything we know about this system. For example, if this is Z1 on an axis, then this would be Z2. And I have a change in height between Z1 and Z2. I can call that height H. What I also know happens to be going on in this system is it looks like it is an open system where mass can flow in and mass can flow out. It's going to be the same mass in and out because it looks like that mass has nowhere else to go. So if I were to look at the change in energy of this system, that's going to be equal to the change of internal energy plus the change in kinetic energy plus potential energy. Well, this system already had some internal energy. So the change in internal energy is going to be the mass flow rate times U2 minus U1. So delta U is U2 minus U1, or mass times the internal energy per unit mass. So this is internal energy per unit mass. I took out mass. Why? Because I know it would be handy if I take out mass from this term. I'm going to take out mass. And then a change in kinetic energy is equal to EK2 minus EK1, which is equal to 1/2 mv squared 2 minus 1/2 mv squared 1. Oops, mv squared 1, but the same amount of mass entered and left, so I can factor out mass and get 1/2 velocity 2 squared minus velocity 1 squared. I factored out mass. I took out mass. Again, I took out mass here. I took out mass here because I know that this is going to help me. Here, change in potential energy, and everybody can write this a different way. E potential energy 2 minus E potential energy 1 is equal to mgh minus mgh, m1 g1 h1, m2 g2 h2. Well, of course, m1 equals m2. M1 equals M2 because there's like the same mass flow rate in and out. Of course, G1 equals G2. It's 9.81 meters per second squared. That's just the acceleration due to gravity here on planet Earth. And it's not really an H, it's really a position. So I shouldn't have put H in there. I should have put a position. This would be Z1 minus Z2. Z1 minus Z2. So I'm going to factor out M because they're the same. I'm going to factor out Z, and I'm going to get Z2 minus Z1. Sorry, I factored out G. Acceleration due to gravity because they're the same. And now I don't like this color. I factored out, I took out mass here, 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 here. So when I sub these back into this equation, I'm going to have a mass here, a mass here, and a mass here. And that's going to help me, and I'm going to be able to cancel them out. So this is how I'm going to do my change in energy of the system. When I see these equations on both sides, I can then start crossing out masses, and then the amount of mass in the system will no longer be relevant or part of our equation, and our calculations get nicely simplified. So I can illustrate how that happens, and I'm just going to illustrate that up here where I have some room, and you'll see why I wanted to take out those mass terms. E in equals E out is another way of saying the first law energy balance. It doesn't matter which way you prefer to say it. I prefer to say it this way. So the internal energy in plus kinetic energy in plus potential energy in equals the internal energy out plus kinetic out plus out. Yes? And then I'm going to take the internal energy. I'm going to take the equations from down here. M dot U1 plus 1/2 M V squared 1 plus M G Z1 equals M. I'm going to remove the dots because I'm just not going to do it as a rate. If I do it as a rate, I just divide everything by time. Every single one of these M's becomes an M dot. MU2 plus 1/2 MV2 squared plus MGZ2. And what I have now is an M everywhere in every single term. So they can all cross out. So what I'm going to end up with then is U1 plus 1/2 V1 squared plus GZ1 equals U2 plus 1/2 V2 squared plus GZ2. And in a problem like this, how will this be applicable? Let's say the question is, what is the change in internal energy of the system if a velocity V1 of fluid comes in and it leaves with a velocity V2, and the height is known? What is the change in internal energy of the system? Then you would solve this by saying U2 minus U1 equals, bring all of these over to this side, substitute, 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 and you have figured out the change in internal energy of this system. So that's the kind of place we're going with this.